What if we told you that a letter, just one letter, could change the course of history? It was the summer of 1939 when Albert Einstein and Leo Szilard penned a letter to President Franklin D. Roosevelt. This letter, known as the Einstein-Szilard letter, warned the president of the potential for atomic weapons. It was a time of global tension, and the United States was not yet involved in World War II, but the implications of this letter were far-reaching. It sparked a realization in the United States government that they needed to act, and fast. With fears of Germany developing nuclear weapons, the wheels were set in motion for the birth of what would become the Manhattan Project. A secret research venture that would bring together some of the brightest minds of the time, with one common goal: to harness the power of the atom. And so, the Manhattan Project, a venture that would forever change our world, was born. Behind every great project, there are great minds. And the Manhattan Project was no exception. It was a veritable who's who of the scientific world, pulling together some of the brightest minds of the time. Central to the project was J. Robert Oppenheimer, often dubbed the father of the atomic bomb. His brilliance in theoretical physics was key in bringing the project to fruition. Next, we have Enrico Fermi, an Italian physicist and the creator of the world's first nuclear reactor. His work laid the groundwork for nuclear power and for the bomb itself. And then there's Leslie Groves, a United States Army Corps of Engineers officer who directed the project with an iron fist. His military expertise and tenacious spirit kept the project on track, despite numerous challenges. These men were the architects of a new era, whether they intended to be or not. Their contributions to science, while controversial, undeniably shaped the world we live in today. Uranium and plutonium, two elements that would become synonymous with the atomic age. The Manhattan Project was a marvel of scientific achievement, but it was also a challenging feat of engineering. At the heart of it all were two elements: uranium and plutonium. These two heavy metals, when manipulated correctly, could release an enormous amount of energy, and it was this energy that the Manhattan Project sought to harness. Uranium, in its natural state, is a mixture of isotopes, predominantly uranium-238. But it's the much rarer uranium-235 that scientists were after, as this isotope can sustain a nuclear chain reaction. The challenge was separating the two, a task that required ingenious methods. Engineers turned to three primary techniques: electromagnetic, gaseous, and thermal diffusion. Each of these methods relied on the slight difference in mass between uranium-235 and uranium-238. The electromagnetic process utilized a device called a callitron, which used magnetic fields to separate the isotopes. The gaseous diffusion process exploited the fact that lighter uranium-235 gas molecules would diffuse through a barrier slightly faster than heavier uranium-238 molecules. Thermal diffusion, on the other hand, was based on the principle that lighter molecules rise faster in a heated gas or liquid column. But uranium wasn't the only game in town. The project also focused on producing and separating plutonium, an element not found in nature but could be produced in nuclear reactors by bombarding uranium-238 with neutrons. The resulting plutonium-239 was then chemically separated from the remaining uranium and other fission products in a complex and hazardous process. The reactors used for plutonium production were located in Oak Ridge, Tennessee, and Hanford, Washington. These sites were chosen for their isolation and abundant supply of cooling water, a critical component in the reactor's operation. Once the uranium and plutonium were obtained, the next step was to design the bombs. Two designs were used: the Little Boy design, which used uranium-235, and the Fat Man design, which used plutonium-239. Both designs aimed to bring about a supercritical mass, triggering a chain reaction and releasing a vast amount of energy. Science had unlocked a new power, but at what cost? With great power comes great responsibility and great risk. As the Manhattan Project advanced, so did the need for stringent security measures. This project was not just a scientific endeavor, it was a race against time, a race against enemies. The United States government ramped up the security around the project, implementing a cloak of secrecy that was unprecedented in its depth. Scientists and researchers were often unaware of the full scope of the project they were working on. Each team focused on its own small piece of the puzzle. But even with these precautions, the threat of espionage loomed large. Soviet spies, intrigued by whispers of a superweapon, were eager to unlock the secrets of the Manhattan Project. The cloak and dagger world of atomic spies added another layer of tension to an already high-stakes endeavor. Despite the best efforts of the security forces, information did leak out, hinting at the espionage challenges to come in the Cold War. Even in the midst of war, the shadows of the Cold War were already looming. The date was July 16, 1945. The world was about to change forever. At the heart of the New Mexico desert, under the cover of darkness, the first successful test of a nuclear weapon was about to take place. Codenamed Trinity, this test was the culmination of years of intense scientific research, tireless engineering, and unyielding determination. In the early morning hours, as the countdown reached zero, a brilliant flash of light filled the sky. The sheer power of the atomic bomb was revealed, its mushroom cloud reaching heights of over 40,000 feet. The shockwave was felt miles away. The landscape was forever altered, melted sand now forming a radioactive green glass dubbed trinitite. But it wasn't just the desert that was transformed that day. The successful Trinity test marked a turning point in human history. The power to harness the energy of the atom, once thought to be the stuff of science fiction, had become a reality. With the successful Trinity test, humanity had entered the nuclear age. August 1945. 2 cities, 2 bombs, a world forever altered. In the early morning hours of August 6th, the B-29 bomber named Enola Gay released a weapon of unimaginable destruction over the city of Hiroshima. The bomb, affectionately known as Little Boy, plummeted towards the earth, exploding in a blinding flash of light and heat, instantly obliterating nearly everything within a 1-mile radius. 3 days later, another B-29, Boxcar, carried a second bomb, Fat Man, over Nagasaki. The explosion resulted in a mushroom cloud that rose miles into the sky, leaving a trail of devastation beneath. These 2 bombings marked the first, and, to this date, the only uses of nuclear weapons in warfare. The immediate aftermath was a scene of utter devastation. Buildings were flattened, fires raged, and an estimated 125,000 people were instantly killed, with tens of thousands more dying in the following weeks due to burns, injuries, and radiation sickness. The bombings led to Japan's unconditional surrender, marking the end of World War II. But the impact of Hiroshima and Nagasaki extended far beyond the physical destruction. The bombings opened a Pandora's box of ethical debates that persist to this day. Questions about the necessity and proportionality of the bombings, the targeting of civilians, and the long-term effects of radiation on survivors and their descendants continue to be hotly contested. Moreover, the bombings marked the dawn of the nuclear age and the beginning of a global arms race that would come to define much of the latter half of the 20th century. The bombings served as a stark reminder of the destructive power of nuclear weapons and the imperative to prevent their use in future conflicts. In the span of a few days, the world had witnessed the destructive power of the atomic bomb. The bombings of Hiroshima and Nagasaki were not just military actions in a global conflict, but watershed moments in human history, forever changing the way we view warfare, diplomacy, and the pursuit of peace. The war was over, but the atomic age was just beginning. In the aftermath of World War II, the world had been introduced to a new kind of power, one that held both the promise of limitless energy and the threat of unparalleled destruction. The Manhattan Project, initially a wartime endeavor, had far-reaching implications that extended well beyond the end of hostilities. The legacy of the Manhattan Project is a complex one. On one hand, the project hastened the end of the Second World War, arguably saving countless lives that would have been lost in a protracted conflict. On the other hand, it marked the beginning of the nuclear arms race and the Cold War, a period of geopolitical tension and near-constant threat of nuclear annihilation. But let's turn our attention to the Atomic Energy Commission. In the immediate post-war period, it became clear that the atomic energy needed to be regulated. Thus, in 1946, the United States Congress established the Atomic Energy Commission, or AEC, to oversee the peacetime development of atomic science and technology. The AEC took over the facilities and personnel of the Manhattan Project, transforming a military program into a civilian one. It was tasked with promoting and regulating the use of nuclear energy. The AEC played a crucial role in shaping the U.S. nuclear program, overseeing the construction of nuclear power plants and the development of nuclear weapons. It also played a key role in international nuclear policy. The AEC was instrumental in the creation of the International Atomic Energy Agency, which promotes the peaceful use of nuclear energy and works to prevent its use for military purposes. The Manhattan Project and the subsequent creation of the AEC fundamentally changed the world. The power of the atom, once a theoretical concept, had become a practical reality with profound implications for society, politics, and the environment. The Manhattan Project not only ended a war but also ushered in a new era of nuclear power and weaponry.